Today we'll see the easy way of transferring a complete IMS database into a relational database and the setup of a bidirectional synchronization. Welcome to a new episode of tcVision Know-How. We start with an IMS sample database in COS. We will load the complete database to Postgres and set up a real-time synchronization in both directions. Our demo environment consists of a CentOS 2.1 with IMS, an Ubuntu server with Postgres, and a Windows 10 for the control board. All components have been connected to each other. We start with the definition of the metadata. For this, we connect both of our managers, on the mainframe and on the server. The tcVision repository, which holds all the replication information, is located in the Postgres target database. Now we input the metadata using different sources. We will create input and output objects, and the links between them. The output target is Postgres. We import from a copybook that we transfer to the PC before starting the import process. We will link it to an object on the mainframe. Our copybook includes all segments. We have to choose one here. Then we link it to the IMS segment. For key information, the DBD and PSB libraries are evaluated. The output schema is named IMS demo data. To get the whole database, we import all the other segments. This process can also be done via command line. Now we can see how the input IMS record is built, how we would create the Postgres table, and how the fields are connected. We let tcVision suggest the create table statements, so it is possible to handle the data modeling in tcVision and create the tables afterwards. The next step is the initial load of the database to Postgres. We choose the most effective way and create an unload of the database using this JCL. This unload is transferred now to the server in binary mode. The transfer can be made via FTP or tcVision itself. Now we create the actual task that handles the transfer. This can be created generically for all unloads. We do a bulk transfer using an IMS unload file. We name the input file that we recently transferred. The output is in state 3, fully prepared for the target database. For the most effective transfer, we use the direct load feature by Postgres. We include the connection parameters for the loader. A connection test returns the version. When running the task, we transfer the whole database to Postgres. The statistic that is written by all tcVision tasks shows the data that's been inserted in each table. To prove the data, we use the Postgres utility psql. The next step is to set up a real-time synchronization from IMS to Postgres. The tcVision data capture function is based on the standard IMS log record type 99. The creation of these records is activated using the exit parameter in the DBD or segment generation macros. The task that reads the log is defined in a mainframe system. We use the IMS log reader feature and select the segments we want to synchronize. We have to specify the name of the DB control region and optionally the name of the write-ahead file to get the changes faster than they arrive in the online log datasets. The data will be sent at stage 0, without any processing to save mainframe CPU cycles. We send the data to our Linux server and the receiver writes the data to a staging area. We start the task. It automatically starts the receiver and connects. Let's do some updates. One of the sample transactions changes the stock. We commit our changes. And we can see that the apply task has been started automatically. It applies the data from the staging area to Postgres. Here we can see our update. The last part is the reverse synchronization back to IMS. For this direction we have to create a new output target, which must be done on the mainframe. We have to enter the suffix of the DRA table and the name of the PSB. We recommend to have one PSB containing all the segments that should be updated by tcVision. Now that both structures, Postgres and IMS, are present, we have to import the input and the output side separately. The Postgres tables as an input can be imported at once. Here they are. The IMS output segments have to be defined one by one. Just as before, we select the segment name and look at the DBD to generate the SSA for the IMS access. This is stored in the output table definition. The output code table is now switched to AppStick. We can see the key feedback area of the parent segments and the key of the current segment itself. When we link the tables, tcVision tries to match the types and names. Only one glitch: the key feedback area of the segments is not used here. All the relevant fields have been linked correctly. Now to the tasks that do the transfer. The reader uses Postgres log as input. Here we can define an additional selection. This is optional. This task will write the data to the staging area, just like it did with the other direction. The files are written by committed transactions. A sender will propagate the data to the mainframe, where our apply task receives the Postgres changes and applies it directly to IMS. The apply task is defined on a mainframe. This task runs in a different region. We define a JCL which is submitted to Jest when the task starts. We start the reader and are ready for some updates now. We got a new shipping and add 10 items to our stock. Here we can see the sender already pushed the data to the mainframe and ended successfully. What happened to IMS? Here we can see the commands to update the segment. A status code of blanks is the one we want to receive. We can also see the keys that the update is built from. What did we see now? With the metadata defined once, we can do a very effective initial load and real-time synchronization from IMS to Postgres. Variable process definition allows using the CPU on the server and then on a mainframe. The reverse replication is easy to define, and of course we avoid to loop back changes made by tcVision itself. Thank you for your attention.